To push 20 million liters of raw water through an 18-kilometer pipeline every single day requires an immense continuous injection of energy. Achieving that target flow rate forces the plant to pump against a massive 202.5-meter static head. The mechanical solution relies on a bank of 650-kilowatt vertical flange-mounted motors spinning at 1480 RPM to drive the turbines. But generating this much force introduces a severe physical threat. Injecting such high levels of energy too rapidly, or losing that energy suddenly, will trigger catastrophic hydraulic shock. When thousands of tons of moving water hit a stationary barrier, the kinetic energy compresses and generates a destructive kinetic pressure spike known as water hammer. This waveform reflects, compounding in amplitude as it travels backward down 17.8 kilometers of PN40 steel pipe. Protecting a pipeline from bursting under these forces dictates every design choice in the facility. The entire electrical, instrumentation, and control architecture exists purely in service of fluid mechanics, engineered to tightly synchronize and carefully dampen extreme physical energies. The process begins at the outdoor structure, where the plant receives its primary power via a 33-kilovolt double-circuit overhead line spanning 18 kilometers from the main utility. That high-voltage current is routed into a pair of 2500 kVA step-down transformers. This specific capacity accommodates the plant's 1102.4 kilowatt running load while reserving a strict 20% margin. This chart plots the electrical grid voltage over time during motor ignition. The 2500 kVA rating provides enough magnetic bulk so that when the massive 650 kilowatt motors draw their starting inrush current, the downward voltage spike precisely halts before crossing a 3% drop limit, preventing overheating. As the line chart dynamically corrects itself and shifts upward, the tap changer adjusts internal coil ratios to feed a perfectly stable 6.6 kilovolts to the motor bus. Moving from the transformer yard into the underground cable trenches, the power is carried by XLPE cables wrapped in a fire-retardant low-smoke sheath. In enclosed concrete trenches, this FRLS layer ensures a localized cable fault won't fill the vital switchgear rooms above with toxic, blinding smoke. Once the power reaches the main indoor switchgear room, it interfaces with a row of withdrawable vacuum circuit breakers. Vacuum circuit breakers, rather than SF6 gas breakers, are deployed here because they demand zero gas handling maintenance and provide the rapid arc quenching required for the frequent starting and stopping cycles of a pumping station. Looking at this logic diagram, we see the facility's secondary selective topology. Two separate 33-kilovolt power lines feed the system. If one line fails, the central tie breaker mechanically closes, rerouting power from the surviving line to all essential equipment. Maintaining two independent transmission lines, dual incoming breakers, and a central bus coupler guarantees that a localized grid failure cannot interrupt the constant supply of raw water. When the plant is ready to pump, the digital start command originates from a hot standby programmable logic controller panel containing two identical parallel CPUs. But the PLC will refuse the command without a physical prerequisite. A hardwired interlock verifies via limit switches that the massive 600mm discharge valve is fully closed. The pump must start against a closed head to keep initial torque demands low. This numerical breakdown illustrates why these motors operate at high voltage. At 415 volts, a 650 kilowatt motor pulls over 1100 amps, necessitating in practically thick copper cables. Stepping the voltage up to 6.6 kilovolts drops current to 68 amps, slashing copper costs and thermal losses. Because the vertical turbines must overcome a 202.5-meter static head, they need to spin at full RPM immediately. This eliminates the need for variable frequency drives, which are typically used to control motor speeds. However, hitting the grid with the raw starting current of a 6.6 kilovolt motor would destabilize the local network. The solution is a flux-compensated magnetic amplifier, or FCMA soft starter, which controls the current without injecting the harsh electrical harmonics that VFDs generate. The FCMA soft starter utilizes opposing magnetic flux, seen here actively governing the energy flow to create a localized impedance. This acts as an electrical bottleneck, delivering a perfectly smooth voltage ramp-up to the motor stators without shocking the mechanical drivetrain. Once the motor reaches operational speed, the mechanical sequence takes over. The 600mm motorized discharge valve begins to open, taking a rigidly timed 5 minutes to transition from fully closed to fully open. Combining the electrical current dampening of the FCMA with the deliberate 5-minute mechanical valve rotation ensures the thousands of tons of fluid in the pipeline gradually accelerate, actively suppressing any chance of sudden hydraulic shock. During continuous 20 MLD operation, physical conditions inside the pipes are constantly measured by field instruments and transmitted via 4 to 20 milliamp signals along armored cables back to the SCADA control room. Volumetric output is tracked by a 600mm electromagnetic flow meter. Utilizing Faraday's law of induction, it passes a magnetic field through the conductive river water, allowing the system to calculate precise flow rates based on the voltage generated by the moving fluid. For depth tracking, radar transmitters are used instead of ultrasonic sensors. Over turbulent water, sound waves from an ultrasonic sensor hit surface foam and scatter erratically. But microwave pulses from the radar system cut straight through mist and foam, reflecting cleanly back to the receiver. If that continuous analog radar signal fails and the wet well runs dangerously dry, a physical fail-safe engages. A hardwired 4-point conductivity switch acts as a deadman circuit. When the water drops below the metal probes, the electrical circuit breaks, instantly tripping the pump to prevent dry running. Below ground, another layer of protection defends the expensive motor hardware. The entire electrical system is tied to buried pits, filled with concrete, salt, and charcoal, driving the facility's earth resistance to less than 1 ohm. This electrical schematic tracks a ground fault scenario in the 6.6 kilovolt system. Instead of allowing unlimited fault current to surge to ground, the energy is forced through a neutral grounding resistor, which acts as a strict bottleneck, capping the current at exactly 250 amps. By capping the fault current at 250 amps, the NGR ensures that a short circuit won't generate enough heat to melt the motor's internal stator core into unrecoverable slag. The motor simply stops, requiring a straightforward copper rewind rather than total replacement. Sustaining a flawless 24/7 pumping operation requires the SCADA system's analog trend tracking to be backed up by these rigid, unhackable physical constraints. The absolute limit test for this architecture is a complete collapse of the incoming 33 kilovolt utility grid while pumping at maximum capacity. The moment the voltage drops to zero, an engineering paradox emerges. The protective relays detect the blackout and issue a trip command to open the vacuum circuit breakers. But the mechanical coils inside those heavy breakers require electrical power to actuate. This is where an independent 110-volt DC nickel-cadmium battery bank takes over. Completely isolated from the AC grid, the DC batteries hold enough stored potential to forcefully punch the breaker trip coils, physically isolating the massive plant circuitry from the dead grid. Simultaneously, the automation layer responds. On uninterruptible UPS power, the dual CPU PLC executes a bumpless transfer. If the primary processor faults due to the power anomaly, the backup CPU assumes total control of the plant logic in less than 50 milliseconds. Transitioning processors in under 50 milliseconds ensures the digital memory holding the valve positions doesn't wipe, preventing the motorized valves from defaulting to a closed position while water is still moving. Out in the pipeline, defluent mechanics are rapidly destabilizing. With the 650 kilowatt motors suddenly dead, the massive column of water halts and reverses direction due to gravity. The falling water tears at the piping, creating immense internal vacuum pressure. In response, the facility's pneumatic surge protection air vessels deploy. Charged by heavy-duty compressors, these massive steel tanks instantly inject compressed air at 30 kilograms per square centimeter directly into the pipeline, acting as a pneumatic shock absorber to physically cushion the reversing water column. In the control room, the SCADA logs the exact millisecond the vacuum breaker valves snap open along the pipeline route to equalize the pressure, confirming the air vessels successfully dissipated the kinetic wave. A catastrophic pipe burst is averted. High-voltage electrical distribution, solid-state processor logic, and rapid pneumatic physics all deploy in a perfectly synchronized sequence to constrain extreme kinetic energy and force a volatile mechanical system into a safe state.